Okay, I'll start, then Marko will take over. It's really interesting and honest presentation. For us, we're actually like a real hardcore Java guys, turned into putting the stuff that we used to build in Java, putting it on our cloud, the OpenShift, which is part of Red Hat's cloud offering. And to do that, OpenShift uses Docker, Kubernetes, and eventually Jube. I'll talk about Jube later on. And yeah, we're tasked with putting Java middleware onto OpenShift. And okay, Marko, take over.
Hi. So how many of you use Docker? Okay, how many of you use Kubernetes? None of you, okay. So maybe I'll fast forward through the Docker part and then put more emphasis on the Kubernetes. So basically, probably you all know that Docker is a platform for building, distributing, and running applications, which basically means it helps you package up an application together with its environment, basically with its OS, file system, something like that, which means that when you deploy your application to one machine and then maybe transfer it to some other, you basically get the same environment, pretty much the same. It basically replaces virtualization, but obviously you can still run Docker daemons, Docker inside VMs if you have large, powerful machines. Basically, Docker allows you, instead of running tens of VMs on a bare metal, it allows you to run hundreds or even thousands of containers, Docker containers per host. One container should basically be one process with maybe its child processes, but you should not combine multiple processes into a single container. So the basic Docker concepts are the following. You have images, where you store them in registries, and then when you run an image, you get a container. So an image is basically a read-only package of an application and its environment, as I said previously. And it consists of layers. This is important because if you have maybe 3 Docker images, all based on, let's say, CoreOS or whatever, and they also share some libraries and so on, you will not need to, they will not take up, each image will not take up its own space. They will be, the files will be shared by the images, if you layer them correctly, obviously. When you create an image, you can push it to a registry. They can be either private or public. There's a Docker Hub registry online, which is basically kind of like GitHub, when you can just upload your own images and other people can reuse them and base their own images on them. And then basically a container, which is a running image, is basically just an image with another read-write layer, file system layer on top of the base image, which allows you to make changes to the file system and obviously run the whole process. This is an example of how Docker layers work. You see 2 Docker containers. One is based on BusyBox, the other one on Debian. And the Debian one is basically made up of multiple layers. The Emacs was added, and then Apache, and then the container was started, which added the additional writable layer. And the BusyBox image was just run as it is, and you get another writable image, writable layer on top of it. So creating Docker images is really simple. You basically use an existing image. You then run a command or multiple commands, even a shell, and then make changes to the file system in whatever way you wish, like installing packages, configuring stuff, etc. When you run a command, Docker creates a new container from an image, allocates the read-write layer on top of that, and executes the command. You can then run additional commands, and then you're able to look up the last container ID. Each container gets its own ID, and you can basically turn a container into a new image, which you can then run, and it starts as from the previous state, right? The easier way to create images is to use a Docker file. Docker file is really simple. You basically just specify the existing image you are basing your image on. You can then add files to the file system, run commands. You can expose ports. That's not so important right now. Add environment variables, which are then exposed to your process, which is running when you run the image. And the command is the actual command that will be run, the actual process that will be run when you run the image. Here's an example of the Docker file for our Wildfly application server. It's pretty easy. It's based on base JDK image, which is also our JBoss image. It sets an environment variable, runs the download command and extracts it, sets some environment variable, exposes 2 ports, and then defines the command that should run when you run the image. So simple as that. Okay, that's the Docker part. So now for the interesting part, that it's Kubernetes. Kubernetes is an open source system for orchestrating Docker containers. It was released by Google, but now a lot of companies are extending it, and one company, one big contributor to Kubernetes is actually Red Hat. Kubernetes provides basic mechanisms for deployment, maintenance, and scaling of your applications. It takes care of auto-restarting, rescheduling, and replicating containers to multiple nodes. That's pretty much it. So the architecture of Kubernetes is basically you have master node or master nodes for high availability, and then you have minions. The minions need to run Docker, and they also include the kubelet, which basically talks to Docker and starts containers, and so on. And then you have the Kubernetes proxy, which basically takes care of routing the traffic to services running on these minions. Yeah, that's it. Kubernetes is really simple. You really have just a few concepts that you need to know about. So basically you have pods, volumes, labels, replication controllers, and services. We'll go over each one in the next slides. So basically with Docker, when you have a host and you run a container, you usually run a container and that's it. Pods are basically a set of containers which, contrary to the default Docker behavior, do share some things. You create a pod in Kubernetes by basically sending a REST request to the Kube REST API. This is a YAML for creating a single pod with 2 containers. One is based on the Docker image dockerfile /nginx, and the other on foo mycooldb. So basically, the containers inside a pod share some resources, and they can communicate. They are not fully isolated as in Docker, and this means that basically each pod gets its own IP instead of each container getting its own IP. So you need to take care of the port conflicts. So you need to know that if you put 2 different containers inside the same pod, you need to take care that they don't use the same ports. So basically, a pod is just like an actual server, actual machine that runs multiple processes inside it. So it has its own IP, and then the processes each bind to their own ports. Kubernetes takes care of containers if they die. So if a container inside the pod dies, Kubernetes will restart it automatically. But if the whole node dies, when you schedule a pod to Kubernetes, when you create a pod in Kubernetes, if the node dies, Kubernetes will not create a new pod. You need to use a replication controller if you want to make sure that a pod, an instance of pod, or multiple instances of a pod are running. Volumes, basically just like Docker volumes, They allow you to share data between containers, and this data can either be when you create a pod. This is an example of creating a pod. You basically define a volume mount, and with the mount path inside the container, and then you define the volume and either mount it to a host directory. In Google's case, you can mount it to the Google Cloud Storage. But there are also other options. One of them is an empty directory, which means that each time you create a new pod, an empty directory will be created, and when the pod dies, it will not be available anymore. So this is not for persistent stuff, obviously. One other volume that has been recently introduced is a secret volume, which is based for sharing secrets between pods. So either passwords, usernames, SSH keys, and so on. So labels are a really important really important concept in Kubernetes. They allow you to basically label anything you can create, any element you create in Kubernetes. So either pods, replication controller, services, and so on. Each label is basically a key value pair. So it's not just a single value, it's a key value, and allow you to categorize things any way you want. So for instance, you can label a pod as its environment is development, production, or either QA. The release running inside the pod can either be stable or Canary, whatever. And you can even partition them across customers. The labels are useful because then you can use label selectors to select a subset of all the pods. And this is basically used by the replication controllers and services, which we'll see next. A replication controller, I said previously that if you create a pod and the pod dies, basically the host running the pod dies, the pod will not be restarted again, the pod is lost. And replication controllers basically take care of that. When you create a replication controller, you basically define the number of replicas you want to have, replicas of the pod. And also you create the pod template, which is then used to create new pods. So each time the replication controller needs to create a new pod, it's going to create one based on the pod template. The labels and label selectors I talked about previously are used by the replication controller to know what pods are the replication controller is responsible for. So the replication controller in this case is responsible for all the pods that have the following two labels. The environment equals production and release equals stable. Pods can obviously have additional labels. That does not matter. Basically, the replication controller just selects all the pods that match these two labels. And if you see at the bottom, the pod template for pods created by this replication controller basically need to have the two labels inside defined, because if they hadn't been defined, when the replication controller would create the pod, it would be missing these two labels, and the replication controller would immediately check if the number of actual instances matches the number of replicas, the requested number of replicas, and it would obviously not match, and it would create another pod, and another one, and another one. So basically, when you create a replication controller, Kubernetes checks if the labels and the label selectors match. So it prevents you from doing this type of mistake. This is just an animation of what basically happens. When you create the replication controller, it checks how many pods with these types of labels are created. It sees that there are none. It also sees that there need to be two, so it creates two instances of pods. Pods are basically right now. Pods are scheduled to any node. There are no. You can implement your own strategies for scheduling, but currently it just sends the pod to any node that's available. So basically, it can even start two pods on the same minion. But you can work around this by, if you bind a pod to one of the host ports, the replication controller will see that it cannot run two pods on the same machine since they both want to bind to, let's say, port 8080. So it's going to schedule them to different machines, to machines that have port 8080 available. Services. So pods and containers inside your deployment obviously need to talk to each other. And to discover services, Kubernetes uses environment variables, and in the future, basically, this is true now. They introduced this, I think, previous week or previous month or something. When you define a service, you basically give it a name. You define the port inside the pod where this service is available at, and you define a port on which this service should be available externally. But externally means inside your deployment, not externally from the internet. You need to do some other things to make it available from the outside. Each pod that gets run after the service has been created will receive two environment variables, which it can look up by name and use the variables to know where the service is located. So it can look up the host and the port of the service. There's also a new option where when you create a service, it gets an entry in the DNS, and basically your pods can simply connect to a service by the host name and a known port, and that's it. Oh, no, I need to say one more thing. So basically, a service obviously needs to know what pods are running this actual service. So again, the label selectors are used. When you create a service, you define the label selector, which basically allows the service to know on which host and which pods, which containers, basically pods, are running the service. So it routes the requests to one of those. The current implementation is just a simple round robin, but you can add your own. What's the time? I think we have time to go over this, yeah. So here's an example of doing a Canary release with a replication controller. So let's say you have one replication controller running, the environment is production, release is stable, it has two instances, two pod instances running. They are both bound to one service called MyApp. And let's say you want to release a new Canary build and move one of the pods to the Canary version. You do that by basically just telling the stable controller to decrease the number of instances you want to have from 2 to 1. The replication controller will immediately kill off one of the services. And then you create a new replication controller, which will take care of the Canary pods. And you set its replicas count to 1. So this replication controller will immediately spin up a new pod with the Canary version. But since the label selector on the service is defined to include all pods that match the environment equals production label, the second pod, the Canary pod, will also be part of the service, and it will be exposed to the outside. So in this case now we have two replication controllers. One is taking care of one set of pods, the other one is taking care of the other set of pods, but the service is basically routing requests to both sets of pods. Now I have another example of, let's say you have a running system and one of the pods consistently stops functioning properly, or maybe after a while all of them do. So how do you basically take the malfunctioning pod out of the production but keep it running so you can do tests on it Because let's say this is a problem that comes up after the pod has been running for 15 days or something. Basically, you can simply, by simply changing the label of a running pod, you can do that through the REST API. You can take the pod out of the subset of the pods that are being controlled by the replication controller and the service. So let's see if I have the... Okay, so for instance, in pod Y2, we will now just change the environment from production, the label environment equals production, to environment equals debug. And since now the label doesn't match the label selector of the replication controller and of the service, the replication controller will stop caring about that pod. It will see that it has only one pod running, and obviously needs to be running 2 since the number of replicas is set to 2. It will spin up another pod with the same label. So environment equals production, release is stable, and the images that are used by in production. Also, the service selector doesn't match the pod we have just taken out of production, and it will basically start routing requests to the newly created pod. OpenShift. So Red Hat is collaborating on Kubernetes, and it has already introduced some new extensions into Kubernetes. One of them are application templates, which basically allow you to prepare a JSON file which contains parameters, and then when you want to deploy your application, it will either ask you for actual values for these parameters or generate them itself. And from this, you basically get an application config JSON, which is then pushed to Kubernetes, and Kubernetes creates all the pods that are defined in the application config. One other thing OpenShift introduces are builds. So basically, it allows you to host source code in your Git repos, and it will automatically perform builds, deploy your pods, and whatever. These builds can be either kicked off by doing a git push, or it can also check if the base image your application is based on changes. So you can configure it so when a base image changes, it will rebuild your own application and run it. Obviously, you don't want to do that automatically. You don't want to get the new version into production automatically. You want it to go to staging or whatever. And that's it from me, so I'll leave it to Aleš.
Oh yeah, with the OpenShift, well, Marko mentioned, like Kubernetes, of course, is not enough. So we need, in order to OpenShift to function properly, we need a bit more, as you already mentioned. So different things about aggregated logging, aggregated metrics, and so on. OpenShift, we went through different versions. This is version 3. The first one was basically when we bought some company and then just relabeled the stuff. Version 2 already had similar concepts of what we see with Kubernetes and Docker and so on. It was just our stuff built on top of Linux containers and so on. But just Kubernetes and Docker makes it a lot more easier. What we did, we had some gears and different stuff. We called it gears, which was pretty similar to what Kubernetes and Docker provide. And version 3, we quickly jumped on the Kubernetes wagon with Google, and just Google are slowly moving things into Kubernetes. All the stuff that they have privately, they're moving into Kubernetes. So, but there are, of course, there's still some stuff missing. For example, in Kubernetes, the stuff with auto scaling. For example, we are targeting Red Hat Summit, which is at the end of June. We have to have these examples of, I don't know, our middleware enterprise application platform nicely running. But of course, in order to do that, we need something like auto scaling. Eventually, auto scaling should be part of Kubernetes. For example, if you think about it, the HTTP layer as it is, of course, the services are the stuff that expose the HTTP to the external stuff, and it's the services, Kubernetes services, that should have the logic of autoscaling. They don't have that yet, so we need to provide something of our own, and that's like I've written a small utility in Golang, I call it autoscaler. It checks, goes to the pods, connects directly to the running container, asks it for the details of the matrix, collects them, recalculates, and see if it needs. But then autoscaling is quite simple, because all you need to do is you sort of have to calculate how much load is there for the containers, and then just schedule it to the replication controller. I need so many replicas that will be able to, I don't know, scale to the stuff that I configured. As it is, there's no aggregated logging, so we had to look into the logspot, logstash. Eventually, we had the fluentd now. In order to aggregate all of this, we have using Elasticsearch, and then to view it, we use Kibana. For aggregated matrix, there is like a C advisor written in C. Hours ago, but then we needed something more custom. There was like, we call it J advisor, because it was sort of like on top of Jolokia, which is a JMX based matrix gathering and so on. But then we combine it into one, and we call it K advisor. Then K advisor pushes stuff into InfluxDB, and then Influx Grafana collects it out of InfluxDB and so on. So that's, but to sort of aggregate all of this and to put it in a proper project, that's what Fabricate is. We have Fabricate, which is part of the FuseSource. We bought FuseSource company like 2 years back. Initial Fabricate version 1 was a big mess, and still is a big mess. It was based on OSGI and all those Karaf and all those things, and it was like a nightmare to sustain with OSGI, nightmare. But with Kubernetes and Docker, it turned out to be really easy. That basically we were able to delete like 80% of the project of Fabricate, and just version 2 is based on, of course, like this talk is about, is based on Kubernetes and Docker. So for EAP, this is what we've been struggling with, or putting it properly into this Kubernetes and OpenShift environment. And, of course, there's a bit more to it. For example, in order to properly scale those EAP containers, you need to have the multicast is not available, so you need to provide our own mechanism, and we call it QPing, which is a cluster discovery mechanism based on Kubernetes. Of course, the information is, most of the information is already there. We just need the bits and pieces for actually EAP clustering. And not to manually test all of this stuff, which is kind of achievement to put it up properly, and then to be able to just to manually test all of this stuff, it would be even a bit too much. So we have something called, we added stuff on top of Arquillian. Arquillian is a JBoss test environment, like a project at JBoss, which sort of abstracts away the notion of containers. So you can run same set of tests, but in different environment, different runtimes, and this is what Arquillian provides. And we've written a extension to it. So for the CE, which is the cloud enablement, this is what our work is all about. Okay, then Jube. Jube comes from Cube for Kubernetes. Fabricate as it is, of course, not everybody has Linux, like most of our company, mostly like Mac and Windows, even though we are like a Linux company, which is funny. But yeah, of course, if you're not using Linux, then you're not able to have, because Kubernetes and Docker are based on top of Linux. But to properly test all of the stuff for Fabricate, you need something more. And this is where Jube came in place. It's for example, if you would want to sort of switch the environments from, I don't know, Mac to, to Linux and all those, it has to be, of course, everything has to be virtual, and it's like a pain, right? if I want to debug it properly, of course you can always debug, but still you need to set up all the routing and so on. It's like it's a huge mess, locally versus remote. And of course, everything that you do is a Docker image where you just want to run your app, like a just really simple app. It's like a var, an ear, or a jar, whatever. You just want to run it. You don't want to have the trouble of recreating all the Docker images, all the layers, then pushing it into some sort of hub and so on. It takes time, right? But then if you want to easily test this, that's where Jube comes in place. And what Jube for the Kubernetes as a user, it's all about the API. It's the REST API that you see. You don't see the details of the Kubernetes. And what we did was we mocked the Kubernetes API on top of as Jube. Like it's all Java based. We have underneath we have Zookeeper to mock the replication controllers. We have master election, like I said, through Zookeeper. Replication controller is always like sort of checking if the replicas are alive and puts it up. So it's for you, for example, the Fabricate as it is, Fabricate talks directly to the Kubernetes REST API. And if you just change it with Jube, the Fabricate wouldn't even notice, right? And if you base your own stuff, for example, on sort of Kubernetes REST API, you can just easily change it with Jube. You just redirect where your Kubernetes master lives, right? And that's it. So, of course, the question is then, where's Docker? Of course, there is no Docker because you don't have Linux, and we sort of have to reinvent the things, and we call it like zip images. It's like you have to zip up the whole container that you want to run. For example, in the case of the Wildfly application server, you zip up the whole Wildfly application server, plus you added lifecycle scripts. First, you have to add lifecycle scripts for all the different environments, for example, for Windows, for Mac, for so on, that then this Jube calls. It just goes and runs the process. There needs to be a startup exe file or startup sh and so on file that the Jube invokes and runs. So it's again, as I said, like there's a pain of creating Docker images. Now you have a pain of creating zip images, but it's a bit easier because what we also provide, we provide a Maven plugin. We just say this is like my parent zip image. I want to have this app, and it quickly bundles it up. There's no uploading into Docker Hub and so on. So it's a bit faster, but it's still, of course, it's a pain. Without the plugin, it would be even bigger pain. Okay, we used to have a demo with this presentation, but since there's no time and so on. But if you really want to see something in action, I have my laptop with me, and we can just show all the stuff. It takes like you run up Jube, Fabricate comes part of it, at least the Hotio, which is the console. It's like AngularJS plugs into it, looks it up. It says, oh, there's an environment variable of where the Kubernetes master lives. It connects to it. It exposes some of the pods and containers and so on. It's like that. And then, for example, we had a Wildfly zip image running inside with an app, with a Hello Servlet app. I can easily form a cluster, just you just put up a bit more, like more than one replica, and you connect to a cluster and so on. So quite easy. Okay, those are the resources. It's of course with Red Hat, it's like 99% of it is like open source, and as everybody mostly these days, it's all on GitHub. So Jube is on GitHub. You can just easily build it your own, or run it, or you can even like download it from the Maven Central. That's the Fabricate. It describes all the stuff from Fabricate 1 to Fabricate 2. Hotio is already also there. Like Hotio is like a super pluggable console for whatever. You have this something like Hotio plugins, and it's all on AngularJS. You can, for example, we had of course Hotio was developed for the Fabricate, but now it's going to be turned into a console for the OpenShift because it's sort of so easy to plug in different things, and that's the Wildfly link. Some of the resources from Marko stock, okay, Docker, Kubernetes. I think, okay, Kubernetes, so far you have 3 implementations of it. Okay, it's like you can always go, and Kubernetes also is on GitHub, you can go and build it on your own. To run it, it's a bit a pain. It's like much easier to run it as part of OpenShift, or Google runs it as part of the Google container engine, right? And there is like a third implementation outside, right? So, but yeah, it's quite easy. What we do is we extend, as I said, like with OpenShift, we extend Kubernetes a bit, more, customize it a bit, and then run it. So that's it. That's the last slide. Okay.
Thanks. Any questions? Anyone? No? Okay.
Okay.
Thanks.
Thanks.